Today we're going to go through we're going to go through electromagnetism, and we're going to go through a couple of examples on circuits. Essentially, the electromagnetisms in the circuits, there's quite a bit of theory involved, and please, once again, I know I keep repeating it, know the laws, because that's important. You will be asked to repeat them, in some cases explain them, and so forth, right? Let us have a look at electromagnetism. You know the principle thereof, and what it's about is if we bring a magnet near a coil, and what I always use in my notes is this as an example here. Maybe you can see it, but I've got basically a slinky spring that's wound around there, and that represents my coil or my solenoid. And if I pass a current down that coil, I will generate a magnetic field, and depending upon the direction of the current, that will give me my north and my south poles of the electromagnet. And ditto, if we bring a magnet in, instead of that we generate a current, right? That's what this section is dealing with. And let's just have a look at an example. What they've said, and hopefully you've got this already. A circular coil has a radius of 2 centimeters, is perpendicular in a magnetic field of 0.5 Tesla, and there are 1500 turns on the coil. Ignore the resistance of the coil, and it is removed from the field in 0.5 seconds, right? So, and they want to know what the induced EMF is. So first of all, let's just have a look at it. Let's just draw it first, because in physics, remember, draw it. Don't just jump into a formula. Draw the states, draw the changes in it. We'll show some of those when we talk about Newton's laws of motion in a different section. But you must draw it, just to clarify your mind. So we say, right, here we go. Here we've got a north pole, and here we have got a south pole, right? And we are drawing our magnetic field is from north to south. Now those lines represent what? They represent the Teslas. That's how many of them are there. So we can say, right, B is the magnetic field, and that is going to be equal to 0.5 Tesla. Okay. Then they've told us, and let's just change color here. They've told us that we've got a circular coil sitting in that field over there. I've just drawn one loop of it, but it's like that basically, isn't it? It's a coil that looks like this, and in this case, it's got 1500 turns. So now we've got that coil, and now we're going to remove it from the field, either to the right or left, or vertically. We're taking it out of the field in a period of time. And the formula from Faraday, well, is we know that we've got the EMF induced is minus N times delta phi over delta T, d phi dt, whichever you prefer. And that's going to give us our induced EMF, isn't it? Well, first of all, we've now got to work out what our phi is, haven't we? So let us work out the area of this coil. So let's say the cross-sectional area of the coil. First of all, we say it has got a radius of 2 centimeters. Okay, so therefore we say the area is going to be pi r squared, correct? And if we now use that there, we can say that's going to be, and the radius in this case was 2 centimeters, which means we're going decimeters, meters. We're going to be dividing by 100, correct? So we're going to have pi times, let's just change that, 2 over 100, 0.02 meters, pi times 0.02 squared, and that gives us pi times 0.02 squared, 1.25 times 10 to the minus 3 square meters. Okay, so we've now got the area, and we know B, and we know that phi is equal to BA cos theta, and in this case we say it's perpendicular, right? Now I hope that you're all au fait with that, but by being perpendicular, it means that the normal to the coil, right? Imagine the coil is here. If I can just show you, let's just have a look at it. Here we go. Here's our setup, right? We've got a north and a south, it doesn't really matter, and there's the coil inside there, and we're going to remove this out of that. But now we know that what we've got to do is we say that the normal to the surface of the coil is parallel to the Tesla lines, isn't it? So the normal to the surface of the coil, let's just put it in green, is there. It's in the same direction, okay? So that means that essentially we've got a maximum, correct? Then now you say, all right, well, where's it a maximum? Well, it must be a maximum. Cos theta, we know, can only be between 1 and -1, and it must be a maximum at 1. And where is cos theta 1? It's at 0 degrees, right? And you can just bang it if you want to check it, and you're going to go then shift cos 0, okay, and you get 90, well, sorry, shift cos of 1, there we go, 0, okay, which means that our normal is going to be sitting over there, all right? So we can essentially ignore that, and we can just call it 1 is equal to B, which is going to be 0. Whoops, let me just get my thing back to black, is going to be 0.5 times 1.25 times 10 to the minus 3, and that's going to give us a phi of 6.28 times 10 to the minus 4. 10 to the minus 4, and we measure phi in Webers. Okay, so now we've got phi. Now please remember that it's delta phi. It means the change in magnetic flux, right? What does that mean? It means in our previous example there, we had this between, it changed from that to 0 because we took it out of the field. Okay, that's critically important to realize. It's a change in magnetic flux. We took it out of the field, right? So we go in physics, and we go final minus initial, it's 0 minus that, which technically gives us a minus sign, right? So therefore we say okay, and it's going to be, let's have a look, minus n, which is going to be, in this case we had our 1800, or did we have 1500 turns, times delta phi. In this case, final is 0, initial is that, so it's going to be times minus 6.28 times 10 to the minus 4, right? And that happened all in the space of 0.5 seconds. And the answer that we get there is going to be equal to 1.88. Okay? Volts. Now, obviously, if we put it back in, we generate the minus 1.88 volts, right? That is where we get the change in the current in our coil, don't we? So, there we've got our voltage. Then the next part of the question is just basically, it's a little giveaway. They say, well, if the coil's got a resistance of 20 ohms, calculate the induced current. All right? Well, that's quite straightforward. We say, right, from V equals IR. V we know is 1.88, and we don't know I, and R we said was 20 ohms. Therefore, our induced current is going to be 1.88 divided by 20, 0.094 amps. Okay? So in any of these, just basically put down, and it doesn't matter which way they come at it, okay? It makes no difference. But put down what you've got. If you know N, if you know volts, perhaps, if you know the amps and the current, you can work back, of the resistance, you can work back to the EMF, the volts, and from there, look at which one. It's the same as any other physics problem. Look at each one and say, what have they given me? But you need to do a quick sketch of the thing. And obviously time is a constraint, so we don't sit there and make neat little, we just make sketches, and the sooner you start practicing making the sketches for yourself, the better. Obviously, if they've made one for you, like in mechanics, you could use that in the exam. Okay? All right, let's have a look at at another question where they say, all right, and in this one, they say a coil is shown below, magnet is approaching and receding, draw the magnetic fields of the coil and show the directions of the currents. What have we got? We've got a south pole. Now, in this case, have a look, we've been given this, haven't we? We've been given a south pole moving in, and they've drawn a section for us, right? Which in essence is a cross section through the wires, right? So there's one wire coming up and another going down. At this point, The reason this section is quite nice is because there's no confusion about which way this thing is wound. Okay, so if it's done in 3D, then look which way it's disappearing. All right, and if you have to explain one of these, then put your explanation down clearly as to what you've assumed. Okay, with regard to directions of coils. Okay, sometimes they are very, very, very misleading actually, and it could be either way. Okay. So let's say we've got a south pole of a magnet moving in. Now what happens according to Lenz's law? What happens here is that the induced current in this coil is going to seek to stop that action, isn't it? It's pretty much the same as Newton's law. To every action there's an equal and opposite reaction. It's kind of the same thing because there's no free lunch in this. You know, you've got to do the work to do something. There's no way that you can't not do the work necessary to overcome the forces. Okay, so let's have a look here. This south is coming in here. What does this magnet do as it comes in? All right, it tries to stop it. So therefore, it's going to induce over here. It's going to induce. Let's just change the color. Okay, let's change the blue. It's going to induce a south pole here, isn't it? Which by extension means that's a north pole. Now what we do in these kind of problems, we're given this magnet's direction, therefore we can say that's a south and that's a north. Therefore if that's a south pole, we're then going to have our magnetic lines coming in because they come out from the north, right? Now instead of in the previous ones we'd use direction of the current that way and the magnetic lines, in this case use it the other way around. Say, right, which way is the magnetic line going? So align yourself to the magnetic line. And if you look at the top, okay, you will see that the top one is going that way around. See? Let's just redraw. There we go. It's going that way around. Therefore, if that's the case, this here must be coming, and let's do it in red. Okay? That must be coming out, right? Because, have a look. There we go. It's going that way around, current at me. Okay. Now on the underneath it, on the just below that one, you see if we put it this way, therefore now the magnetic field is going that way around, therefore the current's going at you. Okay. So therefore on this side over here, it's going that way, and this will be the same all the way up, like so. Okay. And it'll be going that way around all the way, which means that the current is going in and out. Okay, now if we look at the next one, okay, the next one is it's pretty much the opposite, isn't it? And you probably know, I mean you do know what's going to happen. Okay, we're going to have the south pole moving away now. All right, there's our wires over there, like so. Right, so as it moves away, this wants to keep it in place, doesn't it? Right, it seeks to keep it. So what is then? It must induce a north pole and a south pole. Draw your magnetic flux lines going around and in at the south pole over there like that. And let's look once again at the top wire, shall we? The top wire, you can see that the top wire is, my current is going that way. Right, so in this case it's going that way, so it's going in at you. Therefore, this guy up top now is that way. They're all going to be that way. Let's look at the bottom. Align your fingers and you can see at the bottom one, it's coming out at me, isn't it? Okay, see that? Okay, and I forgot to draw my arrows in there, right? Like so. This one's coming out at me, so there we go. Like that. So you've got in, you align it to this. Other way is if they gave you the current, you'd do it that way, correct? But in this case, it's going that way. So therefore, you can see that the current has, in fact, reversed. Okay? So the next part of the question is they say to us, they ask, discuss this phenomenon. Right? Well, basically in this, what you're saying is you're saying that according to Lenz's law, the coil, the solenoid or the coil, seeks to oppose the motion of the magnet, right? Because what is happening is that coming out of this magnet are all these lines of flux, magnetic lines, all the Teslas coming out, right? And as they start cutting the wire, that's what's doing the induced current, isn't it? Right? Because when you start doing motors and things like that, you'll see that they start turning inside the magnetic thing. And as it's chopping through that magnetic flux, it's the same as the coil moving. We're cutting the lines of flux, we then generate the EMF, okay, or the current in there. Now, they then say, all right, discuss it, and basically you talk about Lenz's law, you talk about how it induces it, and as it comes in, it seeks to oppose the motion, therefore it generates a current as per your sketch. And in the bottom one, you'd say it opposes it again and generates a current that way, and then you'd note that you've got a reversal of the current in the solenoid. Okay, so that is the magnetic flux lines. Now, as I've said before, please, when you're looking at these problems, all right, they could, for example, give us a problem. They could say, and this one you haven't got, but let us say they say, all right, we have got, let's say we generate an EMF of 12 volts. Okay, so EMF is 12 volts. And we've got a north and a south over there, like that. And we generate the south, and let's say they give us a delta T equal to, let's think, delta T of, let's say 0.1 second, okay? All right. And then they say, okay, our coil, okay, over here, let's say we've got an area there of 10 centimeters squared. All right, so we would then go and we'll say, okay, then we've got our area. Now 10 centimeters squared, we're going to be moving centimeters, decimeters to meters, and it's the area, right? So we're going up one step, two step, and on an area, each step is 100. Okay, so therefore we're going to divide by 100, divide by 100. Okay, so we say, all right, let's have a look. 10 divided by 100 equals that divided by 100 is that, okay, is 1 times 10 to the minus 3 meters squared. And let's say they give us n equal to I don't know, 1,000, right? And they want to know the strength of the magnetic field. They want to know B, unknown. You see, we've written down all the variables, and all we're going to do now is we're going excuse me, we're going to calculate this. That's the thing with the dry season, isn't it? It gets to us all. Okay, so we've got, let's have a look. We say EMF is equal to minus n delta phi over delta t. Okay, so let's have a look. Well, what can we put in? 12 volts is equal to 1,000, okay, times delta phi over 0.1, right? Therefore, we can now work out what delta phi is. Got to be correct, okay? And delta phi in this case is going to be 12 divided by 1,000 equals that, times 0.1 is going to be, and delta phi is got to be equal to 1.25 times 10 to the minus 3, okay, Webers. Okay, therefore that is equal to BA, phi is equal to BA cos theta, right? Assume once again that cos theta is perpendicular, so cos theta is going to be equal to 1. So I'm just going to leave it out for the moment there. Therefore, we know that that is 1.25 times 10 to the minus 3 is going to be equal to, B we don't know, but A we do. A is 1 times 10 to the minus 3. So we end up working out that B must be equal to, divided by 1, 10 to the minus 3 is going to be equal to, okay, 1.2 Tesla. Okay, so it doesn't matter which way we do it, all right? And yes, the signs there, I have just not bothered about them, okay, because the Tesla is coming out at 1.2. I would have said it's going, this case it's going to be a positive because it's going in, but you could say it's going out of the field, okay? All you do is you put down, and it's the same for any of the other elements, Do a little sketch so that you're sure what you're doing, then put them in over here, right? Very important when you have combined motions one with another one, okay? So, there we go with those, right? We've done a thingy, a magnetic flux one, and we've looked at the current generated, and we've been through the whole solenoid process, right? Those are the typical kind of questions you're going to get in this section. Once again, I know I keep reiterating it, but please make sure that you list all the laws that you have to know and know them.